Hi everyone, this is the continuation of quantum chemistry classes, and in this video we shall learn about the solutions of the Schrödinger wave equation, that is quantum numbers. In the last video we have seen that when you solve the Schrödinger wave equation for hydrogen atom, we got three solutions, and the three solutions are simply nothing but quantum numbers. That is, from solving the Schrödinger wave equation for hydrogen atom, we got three quantum numbers. One is principal quantum number, which is indicated with the symbol n, and azimuthal quantum number, which could be represented with the notation L, and magnetic quantum number, which could be represented with the notation M. So these three quantum numbers are very much helpful in understanding, characterizing the properties of an electron, and that in turn learning the properties and the characteristic behavior of an atom. And shall get into the video, shall go to the in-depth discussion pertaining to each and every quantum number, that is principal quantum number, azimuthal quantum number, and magnetic quantum number. First, we shall consider the first quantum number, that is principal quantum number. See, the principal quantum number will actually say about the energy of the electron. The principal quantum number clearly explains what is the exact energy of the electron which is present in a particular stationary state. And apart from saying the energy of the electron, principal quantum number also gives information about the average distance. Let's say about average distance of the electron from nucleus. This is the two important information what we can get from the principal quantum number value, that is the energy of the electron and the average distance of the electron from the nucleus. See, if the principal quantum number value of the electron goes on increasing, that indicates the electron is moving farther away from the nucleus. Means higher the value of principal quantum number, the electron is present at more distance from the nucleus. And as well, with increase in the principal quantum number value, the energy of the electron also increases. And the principal quantum number value, that is n, can take the values 1, 2, 3, 4, so on. That is, the principal quantum number can always take the integral whole numbers and no fractional value can come. And each and every value of principal quantum number accounts for one stationary state, what we also called as orbit, or also called as shell. So for example, if n is equals to 1, that is called as K shell, and if n is equals to 2, that is called L, and if it is 3, it is M, and n is equals to 4, it is N shell. And like this, with increase in the value of principal quantum number value, the shells will go on increasing. And apart from getting the information about energy of the electron, as well the average distance of the electron at which the average distance at which the electron is present from the nucleus, we can get one more information from the value of principal quantum number, that is each and every shell, that is K, L, M, N. So each and every shell cannot accommodate whatever the number of electrons. Each and every shell has a restriction for accommodating the electron. So the shell can accommodate only a fixed number of electrons, not more than that. So a shell can accommodate how many number of electrons? In order to calculate that, principal quantum number is much more helpful one. So for example, if you consider any shell, either K, L, M or N, whatever it may be, each and every shell, each shell or each orbit or each stationary state can accommodate a maximum of 2n square number of electrons. Not more than this. Each shell can accommodate only 2n square number of electrons, and that we shall look over by applying the rule. So for example, if n is equals to 1, that is k shell. So 2n square, that is 1 square, that is 2. So a k shell can occupy a maximum of only 2 electrons. And if n is equals to 2, that is L shell, that is 2 into 2 square, 2 2's 4, 4 2's 8 electrons. That is n is equals to 2, that is L shell can accommodate a maximum of only 8 electrons. Similarly, for n is equals to 3, that is M shell, it can accommodate 2, 3 square, 3 3's 9, 9 2's 18 electrons. So in this way, we can easily calculate what is the maximum number of electrons that can be occupied in a particular shell, and that we shall see pictorially. Here you can observe around the nucleus there are a definite number of shells, what we also called as orbits, and in each orbit only fixed number of electrons have been accommodated. So for example, in the first shell, that is n is equals to 1, what we also call as k shell, there are only 2 electrons. And in the second shell, that is n is equals to 2, what we also call as L shell, wherein only 8 electrons are occupied. And in the third shell, that is M shell, there are maximum number of electrons occupied are 18 electrons. So that's satisfying the 2n square rule for the occupation of electrons. The second quantum number is azimuthal quantum number, which is also called as angular momentum quantum number. The name itself telling you that from azimuthal quantum number, it is possible to describe about the orbital angular momentum of the electron. Since in an atom, the electron revolves around the nucleus in circular path. And because of its circular motion, each and every electron do possess the angular momentum. And the exact magnitude of the angular momentum possessing by an electron can be calculated with the help of azimuthal quantum number. And the energy associated with the angular momentum of an electron will be always within its total energy, that is determining by the value of principal quantum number, that is n. That means in the last quantum number we said that each shell will be accommodated with a fixed number of electrons. In actual sense, the electrons are not completely grouped in the main energy level only. That means the electrons are accommodated in the sub-energy levels. And regarding that sub-energy levels, we can get the information with the help of azimuthal quantum number. So here I said each main energy level will be consisting of a definite number of sub-energy levels. So in support to this explanation, we can take the help of one simple experiment, that is hydrogen spectrum. So we have seen in hydrogen spectrum, there will be a certain definite number of spectral lines creating various series, that is Lyman, Balmer, Paschen, Brocket, and so on. And you might have remembered each series will be having certain definite number of spectral lines. But in actual sense, the single spectral line is not a single line at all. It actually composed of a bunch of spectral lines. A group of spectral lines will combine to give that single spectral line, and that we call it as hyperfine actually. I mean, each single spectral line will be having certain line, that each spectral line is having bunch of spectral lines. The answer is how the electron, when the electron is taking transition between higher energy level to lower energy level, between this transition there occurs various transitions between the sub-energy levels of the main energy levels. And because of the transition of electron which is happening between the sub-energy levels, we are getting that hyperfine spectral lines that are collectively composed to give a single spectral line in case of hydrogen spectrum. And based on this, we can confirm that each energy level is having certain definite number of sub-energy levels. We can also call them as subshells. And the number of sub-energy levels, subshells that are present in a particular main energy level is completely dependent on the value of n. For a particular value of n, say for example, for a particular value of n, for a particular value of n, L can take the values starting from 0, 1, 2, so on up to n minus 1. And that is what we said, the energy of the azimuthal quantum number or angular momentum will be not more than that of its total energy, that is principal quantum number value. So that for a particular value of n, the azimuthal quantum number L can take values starting from 0 up to n minus 1. And for a particular energy level n, the various sub-energy levels will be designated. Say for example, if L is equals to 0, for that the sub-energy level is designated as S. If L is equals to 1, the sub-energy level is designated as P. If L is equals to 2, it is designated as D. And if L is equals to 3, the sub-energy level is designated as F. So S, P, D, F are the sub-energy levels for, based on its azimuthal quantum number values. Okay, and we said the azimuthal quantum number is actually more helpful in calculating the magnitude of orbital angular momentum of the electron, right? So now we shall see how to calculate or how to check the magnitude of angular momentum of an electron in a strictly speaking way, orbital angular momentum of the electron. The orbital angular momentum of the electron, the orbital angular momentum, in a strictly speaking way, we can say the total angular momentum, or we can simply call it as orbital angular momentum of an electron, is simply indicated with the symbol capital L. And capital L is equals to h by 2 pi into square root of L plus 1. This is the formula we can use for calculating orbital angular momentum of an electron. And in the previous videos we said that h by 2 pi can be written as h cross. So equation can be modified h cross into square root of L plus 1, wherein L is the azimuthal quantum number value. So for example, if the value of n is equals to 2, if the value of n is equals to 2, L can take the values starting from 0 and 1. Since n is equals to 2, and just now we said L can take the values up to n minus 1. So here n is equals to 2. 2 minus 1 will be 1. So here the azimuthal quantum number values for n is equals to 2 cannot exceed 1. Okay, so here the value of L is 0 and 1. If the value of n is equals to 3, it can take the value starting from 0, 1, and 3 minus 1 will be 2. So the L values will restrict up to 2 only. And now we shall calculate the orbital angular momentum of an electron which is present in 2p orbital. So 2p orbital, so here the n value is 2 and we are having p subshell, and for p the L value is 1. So L is equals to 1. So we can calculate the total angular momentum, that is h cross into square root of 1 plus 1. So it will be 1 plus 1 2. So h cross into root 2, that is the value of the orbital angular momentum of the 2p orbital. So similarly, we can calculate for one more orbital. Let us go with 3d orbital. So for 3d orbital, we shall calculate the orbital angular momentum. Here the value of n is 3, and for d, the L value is 2. So L is equals to 2 for the d subshell, and for this we can calculate the value of orbital angular momentum, which is having the formula h cross into L of L plus 1, and h cross, the value of L is 2, so 2 of 2 plus 1. So 2 plus 1 3, 3 2 is 6, so root 6 into h cross, that is the orbital angular momentum value of the 3 electron present in 3D subshell. Like this, it is possible to calculate the orbital angular momentum of an electron with the help of the azimuthal quantum number value of the electron present in a particular subshell. And apart from knowing or determining the angular momentum of an electron, the azimuthal quantum number also helpful, or it gives information. The azimuthal quantum number value will give information about shapes of the orbitals. Azimuthal quantum number will give information about shapes of orbitals in which electron is actually located. So on which subshell or in which orbital the electron is actually located, the exact shape of that orbital can be evaluated with the help of azimuthal quantum number value. So for example, if L is equals to 0, if L is equals to 0, that is S subshell that is having spherical shape. The S orbital is having spherical shape. And if L is equals to 1, that is P orbital that is having dumbbell shape. And if L is equals to 2, that is D that is having double dumbbell shape. And if L is equals to 3, that is F, in actual sense the structure or the shape of the F orbital is too complex, but when the F orbital can maximum accommodate, let me say in this way, an S orbital can accommodate a maximum of 2 electrons, and a P orbital can accommodate a maximum of 6 electrons. Sorry, an S subshell can accommodate a maximum of 2 electrons. A P subshell can accommodate a maximum of 6 electrons. Similarly, a D subshell can accommodate a maximum of 10 electrons. And okay, now we shall move on to the third quantum number, that is magnetic quantum number. And in the last quantum number, that is azimuthal quantum number, we said each electron has a definite value of angular momentum, so that we can compare the motion of electron to the flow of electric current through a loop. So when the electric current is moving through a loop or moving into a loop, we know that when the electric current is moving in the loop, it creates a magnetic field. So we can compare the same condition to the electron which is revolving around the nucleus with a definite value of angular momentum. And since the electron is revolving around the nucleus, it creates a magnetic field, and that magnetic field can interact with the external magnetic field or the electric field. And because of the interaction between the magnetic field generated by the electron with the external electric or magnetic field, there occurs the electrons in a particular energy level, or we can say in sub-energy level. In particularly, the electrons present in a particular sub-energy level will themselves orient to a certain regions. I repeat, due to interaction of the magnetic field created by the electron because of their orbital motion with the external magnetic field or external electric field, the electrons present in a particular sub-energy level will get orient themselves in certain specific regions of the space around the nucleus. And those regions of the space which are present around the nucleus are actually called as orbitals. That is the exact definition of orbitals. I repeat once again, because of the interaction of the magnetic field generated by the electron with the external magnetic field, the electrons present in a particular sub-energy level will orient themselves in a certain specific regions of space around the nucleus, and these regions of the space are called as orbitals. And the magnetic quantum number will actually explains about, that means the magnetic quantum number will actually explains about the number of orbitals that are present in a given sub-energy level, that we can get from the help of magnetic quantum number. That means M will gives information about the number of orbitals present in a given subshell. Whatever the subshell in which the electron is present, how many number of orbitals are present in that particular subshell can be obtained with the help of the value of magnetic quantum number. And the magnetic quantum number M actually depends on the value of the azimuthal quantum number, that is L. For a particular value of L, M can take the values between -L, 0 and up to +L, and the whole and sole variation can take a total of 2L plus 1 number of values of magnetic quantum number for a particular value of L. And that we shall see by considering a simple example. If the value of N is equals to say 3, if the value of N is equals to 3, L can take the values 0, 1 and 2. Right. So for a particular value of L, for a particular value of N, L can take the values 0, 1 and 2. And now we said for a particular value of L, M can take the values starting from -L up to 0, and for a particular value of L, M can take the values starting from -L through 0 and +L till 2L plus 1 as a total. Right. So here we have the value of L, that is 0. That means for the value of 0, M will be once again 0. So overall we are having only one orientation. So there are only one orientation, that is only one orbital is present. L is equals to 0 means we know that it is S subshell. In S subshell there will be only one orientation, that is only one orbital is present in all the three coordinates x, y, z. So the only one orientation is there. Like this is the shape of S orbital, which is spherical in shape, and as we said, it has a single orientation, means it doesn't confine to any one axis. It is coming under all the three Cartesian coordinates. And for L is equals to 1, the subshell is P. And for L is equals to 1, M can take the values. So for L is equals to 1, so we can start with negative term -1 through 0 up to +1. So overall we are having 3 orientations. That means in a P subshell we'll be having a 3 orbitals. And hope you remember, when you are writing the box electronic configuration for a P subshell, we used to write 3 boxes, right? So that means this completely accounts for the subshell, and in that subshell we will be having 3 orbitals. One is Px, Py, and other one is Pz. So we said the shape of the P orbital is dumbbell, and the dumbbells in Px, the dumbbell is oriented in x-axis. Here it is in y-axis, and here it is in z-axis. That we shall see. In this diagram, we can see that we have 3 orbitals, Px, Py, and Pz. In Px, the dumbbell is oriented along x-axis, and in Py, the dumbbell is oriented along y-axis, and in case of Pz, the dumbbell is oriented along z-axis respectively. So that in a P subshell we are having 3 orientations wherein the dumbbells are oriented along x, y as well along z-axis respectively. And when L is equals to 2, we know that it is D subshell, and for a particular value, that is L is equals to 2, M can take the values -2, -1, 0, +1 and +2. So overall we are having 1, 2, 3, 4 and 5. Totally we are having 5 orientations. Totally we are having 5 orientations, and we said a D subshell is having double dumbbell shape, and that D subshell will be oriented in 5 ways. So that we will be giving 5 orbitals. So that we know that in box diagram for a D subshell we'll be writing 4 boxes, right? So one is dxy, dyz, dxz, dx square minus y square, and at last it is dz square, right? So these are the 5 orbitals because of 5 orientations that are present in D subshell. So that we shall see. In this picture, we have the 5 orientations for the D subshell. In this, the 2 dumbbells will be aligned either between the axis or along the axis. In this, the first one, dyz, wherein the 2 dumbbells are aligned between y and z axis. And number 2, in dxz orbital, the 2 dumbbells are aligned between x and z axis. And number 3, the dx square minus y square orbital, wherein the 2 dumbbells are aligned along x and y axis respectively. And number 4, the dxy plane, wherein the 2 dumbbells are aligned between x and y plane. And the last one and a special one, that is dz square, wherein it is having dognut shape or a collar shape structure. And that's about the orientations of orbitals in a D subshell. The last and fourth quantum number is spin quantum number. Actually, by solving the Schrödinger wave equation for hydrogen atom, we got only 3 quantum numbers, that is principal, azimuthal and magnetic quantum number. This is not obtained from the wave mechanical treatment actually. This quantum number arises just because of the spinning of the electron. That means, along with the rotation of electron around the nucleus in circular path, the electron used to rotate about its own axis, and we used to call that as spinning of the electron. And because of its spinning, the electron actually acts as a tiny Bohr magnet, so that it develops a magnetic field around it. And because of its spin motion, in analogy with the orbital angular momentum of the electron, for the spinning of the electron also, we can calculate the spin angular momentum for the electron which is present in an orbital, and the magnitude of spin angular momentum of the electron. Spin angular momentum. Spin angular momentum of the electron can be calculated as capital S is equals to, once again the same, H cross is equals to S of S plus 1. And what is this S? This S is the spin angular momentum. And what is this S? The spin value of the electron. So in order to know what is the exact value of spin value of the electron, or to know the exact value of the spin value of the electron, we should take the help of Stern-Gerlach experiment. And according to which, because of the spinning of the electron used to create a magnetic field B. And the magnetic field may take the upward direction or it may take in downward direction. And the upward direction of the magnetic field will take a value that is ms is equals to plus half. And for the downward direction of the electron, that is a magnetic field, ms can take minus half. So the spin value may be plus half or minus half depending upon the direction of the magnetic field created by the electron because of its spin motion. And if the component S is having the upward direction, the magnetic field is having upward direction, when you calculate the value of spin angular momentum, and if the component of S is in the direction of magnetic field B, which is specified by ms is equals to, okay, so here the ms which is given by plus half, that indicates the upward direction, that what we indicate the electron in this value. For that, the S will be having plus half. And for ms is equals to minus half, we indicate the electron in downward direction, that is S is having minus half. Okay, that means the spin quantum number value, that is S, will indicate the rotation direction of the electron, the rotation of spinning of the electron. If the spin quantum number value of a particular electron is a plus half, that indicates the electron is revolving in revolve. If the value of S is plus half, that means the electron is spinning in clockwise direction. And if S is minus half, the spin quantum number value for a particular electron, then the spinning of electron is in anti-clockwise direction. Okay, so by knowing the total spin value of the electron, it is possible to calculate spin angular momentum of the electron. That means if you want to calculate the value of electron present in 2s orbital, if you want to calculate the spin angular momentum of an electron present in 2s orbital, let me take 2s1. For this, I can write the box electronic configuration. Only one electron means that will be having only positive spin, for which we can calculate the spin angular momentum, that is h cross into s of s plus 1. And here the electron is having upward direction, so that the s value will be plus half. Therefore, h cross into square root of half into half plus 1. So that h cross into square root of, this will be how much? This will be half plus half, that will be 2 plus 1, 3 by 2. And whole and solely, this 3 by 4. This will be 3 by 4. Therefore, h cross into root 3 by 2. That is the value of spin angular momentum. That is the value of spin angular momentum. So, when the value, when you are calculating the spin angular momentum of the 2s1 orbital, when you are calculating the spin angular momentum of the electron present in 2s orbital with the upward direction, the value of s will be plus half, so that on substituting the value of plus half at the place of s on doing the calculation, we got the spin angular momentum value, that is h cross is equals to root 3 by 2. And this way we can calculate the spin angular momentum of the electron with the help of spin quantum number value just by looking over to whether S is plus half and minus half. So we shall go with one more example so as to calculate the spin angular momentum. So 2p3, for this we are supposed to calculate spin angular momentum. So for which we shall draw the box electronic configuration, 3 electrons. So we should accommodate the electrons in this way, and here this plus half and plus half. So each electron will be, all the electrons are in upward direction, so we'll be having plus half, plus half, plus half, right? So the S value will be, so this one half plus half will be 1 plus 1 by 2, that gives 3 by 2. 3 by 2 is the value of ms, and this ms, that's nothing but s or small s or ms, that will be 3 by 2. And for this we need to calculate the spin angular momentum, that is h cross into square root of s plus 1, and here the s value is 3 by 2. So now h cross into square root of 3 by 2 into 3 by 2 plus 1, and that's equals to h cross into square root of 3 by 2 into 2 plus 3, that is 5 by 2, that's equals to h cross into square root of 5 3 is 15 by 2 2 is 4, right? So that is h cross into square root of 15 by 2. That is the spin angular momentum of the 2p orbital. Like this, we can calculate the spin angular momentum for any electron present in any orbital. And in this way, by knowing the value of principal quantum number, by knowing the value of azimuthal quantum number, magnetic quantum number and spin quantum number, we can know what is the exact characteristic properties of a particular electron present in a particular main energy level, or it may be in sub-energy level, or maybe in the orbital, and for which we can understand all the properties so that the learning of chemistry behind the material becomes more easier.